Hello, everyone. Welcome to the Edexcel Physics session before your exam on Monday. Right, guys, let me just quickly do a little bit of setting up here. Just give me a second. Right. So we are doing this lesson today for those who are doing Edexcel exam board. We are doing a separate one tomorrow. I think it's 5 to 7 p.m. for those who are doing AQA. Right? So can you hear me, guys? And just send me a message or something in the chat if you can hear me well and if you can see my board. Good. Thank you, Grace. Hello. Okay. Again, Tiara. Good. Thank you, Jaturna. Okay, right. I think everybody can hear me well. So here's what we are going to do, guys. Now, I've looked into the things that we normally get a lot in this GCSE Edexcel papers. And these are some of the most common things you get. So under the energy, forces doing work topic, work done, power, efficiency, kinetic energy, GPE, energy transfers. Forces and their effect, resultant force, Newton's laws, F equals ma, weight equals mg, and stopping distances. Electricity and circuits is a very popular set of questions. Charge, current, I equals Q over T, potential difference, resistance, all that. Then magnetism, magnetic field, electromagnets, motor effect, Fleming's left-hand rule, all that. Then electromagnetic induction, induced PD, transformers, and national grid related questions. Then particle model, density related questions, specific heat capacity, specific latent heat, and gas pressure. Grace, this is concentrating on Edexcel. So today we are doing Edexcel. Tomorrow I'm doing a QA specific one. Yeah. And guys, another thing, this lesson, so this session, it's going to go for 2 hours. So from 7 to 9. So 7 to 8:15-ish, roughly speaking, we are going to go through the content that is common for both AQA and, sorry, my bad, I shouldn't have said that, those who are both combined and triple students. So this content is for everybody. Then in the last 45 minutes, I'm going to do triple only content. If you see on the top right-hand side, moments, levers and gears, static electricity, electric fields, charging by friction, earthing, pressure in fluids, P equals H rho G and all that, and upthrust, gas laws and generators. And then forces and matter, Hooke's law, elastic deformation, no elastic potential energy, all that. Then elastic potential energy. Right. Yeah, thank you. Welcome, Medavi. Right, guys. So these are the things that we are going to concentrate on. Now, I'm going to do most of these through questions because your exam is literally around the corner in just, 2 days, right? Yeah, 2 days. So we need to do this lot of questions to understand it. But having said that, if you ask me in the chat and if you want any particular help, if you tell me you need certain questions, you want me to explain Newton's second law, or if you want me to explain something, I will explain. This is not exactly aimed for Edexcel IGCSE, but a lot of topics overlap. Yeah? Yeah. So, but it is mainly, I'm mainly looking at my students from the UK who are concentrated on this Edexcel GCSE law, but I know a lot of private schools and some grammar schools here do IGCSE. So, but it's the same exam board, like I said, and these are the content mainly that we are looking at. Yeah. And feel free to message me, guys, in the chat so I can just see, anything you want me to explain, I can explain. Right. So we are quite free. I can just see what I need to help you in this time, and we'll take it from there. Right. Now, let me just quickly show you another thing. Now, these formulae are the main things you guys need to know. So if you look at it, work done, E or W equals F times D. GPE equals mgh, kinetic energy, all that, right? Now, I did not put the triple only ones here. So these are the other ones. The one that is kind of hidden here is half kx squared, just behind my video. I think for some reason, guys, this is only my, I think about fourth live lesson or something. I'm not entirely sure how to move. I think I cannot move it here. If I do it through OBS, I can, but I'm just using directly YouTube at this point. So the formula is kind of behind this. The only one hidden is half kx squared. If you want, just take a screenshot, guys. These are the things you need to know for everybody, combined science as well as triple science. Right. Yeah, I will do certain things related to that as well, guys. Yeah, please let me know. Now let me get the triple only bits here. So here you can see the moment stuff is triple only. For AQA, actually, it's for both combined and triple, but here it's on triple only. Principle of moments. Pressure, this is the Boyle's law stuff. P1 V1 equals P2 V2. Transformer ratio calculations could be actually combined as well. Pressure in the liquid, P equals H rho G, and the basic pressure stuff. So these are the things that you need to know, right? Thank you, Sagat, for the message. Good. Right. Now, so anybody who came just now, I can see the numbers are going up. So we just started, we are just going to look through mainly these content. But having said that, right, if you ask me any particular thing, if you want me to explain anything, just ask me, right? I've been teaching Edexcel since 2005. Yeah, 2005, right? Long time now, 21 years of this, and I've been teaching since 2003, but Edexcel specifically since then. So I've been through 3 different specifications, like every 7-8 years they tend to, not 8, yeah, around that, they tend to change all that. So if you tell me any theory part, I'm more than happy to help you guys. Right, any questions up to this point? So that's the plan. 1 hour and 15 minutes on, then combined content, then triple content, but the combined content is for everybody. If you have any questions, ask me, all that, right? Thank you, Gagana. Right, let's get started then. So I'm just going to get questions and then we will answer these questions mainly. Let's have actually, before we do that, let me just quickly show you some of these theory bits. I'm just going to take one here. Now, let's take one part and then we'll work on this. And then we'll do questions on that. So, energy, forces, doing work. So guys, work done is force multiplied by distance. Now remember, in physics, you have an object, say the force is F, and you move it through a certain distance d. The work done is given by W is equal to F times d. Now remember, this can be a little confusing because moment is also force times distance. But hang on, how does this work with that? Because in moments, it is the force multiplied by the perpendicular distance between the pivot and that, which creates the moment. This d, I know it's also FD, so people can get kind of confused, but please don't do that. So here, this is force multiplied by the distance moved in the direction of the force. Power. Guys, give me the definition of power in the chat. Yes, we will have a look at everything in this topic, yeah? Give me the definition of power, guys. Somebody, come on. Interact as much as you can, guys, because that is the best way to learn. So, definition of power, somebody. Rate of energy transfer, key state. Yeah, that's right. Thank you. So, power is energy divided by time, or work done divided by time, guys. Any of those two things, fine. Thank you. So, energy is measured in joules, time is measured in seconds, power is measured in joules per second. There's another unit for power. Can somebody tell me what that is? An alternate unit for power. What's that? Power is measured in joules per second, and come on, guys, everybody, watts. Thank you. Right? And it's also measured in watts. Well done, Ayan. Thank you, Jatin, Tiara. Good, good, good. Named after James Watt. It's measured in watts as well. Capital W. Efficiency. Efficiency is basically useful output divided by total input. Now listen up, guys. Let me give you a very, very simple example to quickly explain it. Imagine a car, and you provide, let's say this is a normal petrol car, and you give 1,000 joules to as the input by chemical energy. Now, it gives out different forms of energy. Let's say it gives out kinetic energy, 600 joules, thermal energy, because it heats up, say 300 joules, that's 900, and let's say sound energy, the remaining 100 joules. Now, what is the efficiency of this car? So the useful output. Now, kinetic energy, that is useful because the car is moving, that's what we need. What about thermal energy? Not really. I mean, we kind of use it to heat the compartment of the car in the winter and all that, but not the intended use. Yeah, thank you, Tiara. Sound energy? Nah, not really useful. I mean, in fact, most new cars are very quiet compared to the older cars. If you think about older cars from 1960s, 70s, they're like really loud, right? They waste a lot of energy. The new ones don't. So the efficiency is useful output 600, total input 1,000. The answer is 0.6. That's it. Right. Now, thank you, Ayan, for the message, 60%. Now, here's the thing. You're okay. You will get away with it. But if the question was to give the percentage efficiency, then you give it as 60%. If the question is just efficiency, go with 0.6. Thumbs up if you understand this. Efficiency, give the decimal or the fraction. Percentage efficiency, you multiply it. Many students give percentage efficiency when the question is just efficiency. It's not a big deal, but that's not really what is expected. The mark schemes contain 0.6 if they're asking the efficiency rather than percentage efficiency. Yeah? Good, good, good. Moving on. That's fine. Kinetic energy. Kinetic energy is the energy obtained by a mass because it's moving. Okay. So the formula is half mv squared. Really interesting question. Half mv squared. GPE is the energy obtained by a mass due to its height in a gravitational field. Somebody give me the formula for EPE. GPE, I mean. Come on. GPE equals. Come on, send me the 3 letters. Thank you, Tiara. Thank you, Ayan. Thank you, Jaturna. MGH. Yes. MGH. All that. Right. Energy transfers, we were just talking about how, we kind of discussed about it already. I think that's quite sufficient as the theory recap. Let's quickly do an exam style question. So this is how we are going to work on this, guys. I'm going to get the question on the board, and I'm going to give you a couple of minutes to try this. And then I'm just going to go through this. Let me run a timer. Give me a second. Guys, please make a start on this question now. I think for this particular question, you will probably need about, let's start with 2 minutes, yeah? The time is running, guys, so you can see this one. Is the question large enough? Can you manage to see this, everybody? Please let me know. Is that legible? Can you read it? Can you manage with this? Good, good, good. Thank you. Right. Let's do this one. Thank you, Ethan. Right. So if anybody came just now, because I can see the number of students have gone up, we are just discussing through sections of theory that you are likely to get in your exam on Monday, and then we are doing mixed exam questions directly related to that. Yeah, that's what we are doing, and I'm running a time on the board, so you guys can try it independently. Eshal, this is actually Edexcel mainly. I'm running a separate session for AQA people tomorrow. Sunday from 5 to 7 p.m. I'm running a separate live session for anyone who is AQA. This is for Edexcel mainly, but there's an overlap, but there are some differences. Yeah, no problem, Eshal. Tomorrow 5 to 7. Yeah. Edexcel GCSE, I'm not running a separate session because majority of my students are either AQA or Edexcel. I mean, in fact, I used to be a high school teacher in Central London for some time in Whitechapel, then in Harrow for the past 7 years. Now I'm working in a school in college, actually, in Aylesbury in Buckinghamshire. So, and I'm a tutor. A lot of my students are from those two examples. Yeah. Right. Let's do this. Right. Time's up, guys. Let's have a look. A person pushes a shopping trolley with a force of 35 newtons across a car park. Okay. So I'm just going to make this a little smaller. One second. Because it makes it easier to do this, guys. 1 second. Right. A person pushes a shopping trolley with a force of 35 newtons across a car park. The trolley travels a total distance of 48. Okay. Now here's the trolley. The force exerted is 35 newtons and the distance it travels is 48 meters. Okay. Now, calculate the work done by the person. So work done is simply force multiplied by distance. Force is 35. Distance is 48. Yeah. Please send me the answers in the chat, guys. Okay. 35 times 48. It's 1,680. Thank you, Tiara. Thank you, Ayan. Good. 1,680 joules, units, and that one. That's it. The person then pushes the trolley up a ramp into the supermarket. Okay. So it goes up a ramp like that. The ramp is 4 meters long. Okay. So that's 4 meters long, the length of it. Yeah. We'll see. And the height here is 0.8 meters. All right. The mass of the trolley is 22 kilograms. Let's say the trolley is here, and that one is 22 kilograms. Calculate the gain in GPE of the trolley. Okay, so what's the formula? Gravitational potential energy is mgh. M is 22, G is 10, H is 0.8. Guys, two important things. Listen. One, the question says to take the GPE as 10. Now, some of you would know the more accurate value. Send me in the chat. What is the accurate value for GP? The value of lowercase g, gravitational field strength. What's the correct value? 9.8 or 9.81. Thank you, guys. Chaturna, Aisha. Okay, everybody, Tiara. Good. So it's 9.8. But if the question says to go with 10, go with 10. Having said that, usually, if you put 9.8 instead, you are still going to get the mark. Usually the mark schemes allow it because it's a more correct exact value, but don't bother, just do what the question says. The question says 10, go with 10. So 22 times G is 10 times. Now guys, the second important thing is the height here is the height it gains here, not the distance it travels like as it goes along the ramp is 0.8. So 22 times 10 times 0.8 gives me 176 joules. Thank you, guys. Thank you, Tiara. That is the correct answer. Thumbs up or give me some sort of a signal if you got this right. Go on, guys. You can do the. I think I allowed the. Yeah. Okay, great. Good. The work done pushing the trolley up the ramp is greater than the gain in GPE. Suggest one reason why. Now, guys, listen. You push this along this one, you need to do more work than 0.8. Why? Can somebody tell me very, very briefly in the chat? What do you think the answers are? Not exactly, Tara. There are a few other things that you need to think about. Come on, just send me the answers, guys. Why do you think it is? Akradas, I think for in your exam board, waves was mainly paper 1, right? I can double check. Physics 1, 17, 18, 19. Yeah, waves and EM spectrum is mostly like 18. That is paper 1. Yeah? Right. So, that's fine. Okay. Well, here's the reason, guys. Now, let me type this up. Yes, friction, Yaturna. Yes, a good one. Yeah. Surface the ramps or more forces. Okay, let's say. So when you move it, you need to do work against friction, right? So let's write this down. Work is done against frictional friction. So some energy was converted to waste forms like thermal and sound. Yeah. Now, if someone is moving a shopping trolley up a ramp, you can hear it, right? Imagine you're not looking at that, you are somewhere else, but you can hear it. So that is sound energy. And where does that come from? From the person's energy, right? The guy who is pushing it. So things like that. The work done against gravity is actually what is included in GPE. So I wouldn't go there, Demola. Do you understand? Yeah. Air resistance, agree with that. Yes. I can tell that air resistance also, there is work done against air resistance or friction between the things. Yeah. Something to that effect, guys. Done. Any questions up to this point about this energy stuff that we've done so far? Right. No. So let me just clear the board. Now, let's quickly go back to this one. So this is what we've been discussing. So we just discussed about the first part here. And the second one is about the resultant force and things like that. So remember, the resultant force is the force or the overall force on an object. So if you have multiple forces, you can subtract, if they're opposing forces, say 20 to right and 5 to left, the overall is 15 to the right, like that, right? That is a proper definition, but you don't really need that one, but you're fine with this. And Newton's first law, second law, and third law, really important stuff. And F is equal to ma, weight is equal to mg, the formula, and stopping distance stuff. So let's start another question. This question is slightly long, but it's a good question. So This is also related to the energy topic, guys. I'll make it as large as I can. Now, sometimes the way it looks, the image, like the shared screen for me, could be different to how it looks to you. Guys, can you see it? Is that legible? Can you manage to see it, guys? Thank you. All right, let's do that. This one has a couple of different parts. Thank you. And right, 4 parts, A, B, C, D. So I'm going to give you about 3 minutes here. So let me run the timer for 3. And let's do it. If you need any help, you can ask me. In the meantime, if you want me to explain any theory parts, if there is anything that you want me to really quickly talk through, guys, I can do that. Just ask me in the chat, and I'll do that. And by the way, when you have the answers, can you please just let me send them in the chat so I know. I'm looking at the chat right now, guys. So when you do part A, send me the answer, then part B, then part C. You don't need to wait to like send them all at once. So send them one by one. That's enough. Yeah, that's good. Good. So this one is a slightly challenging question because it talks about not just simple energy calculations, but it talks about energy transfers, how it goes from one form to another and all that stuff. Big Bang Theory is actually in Astropart. So radioactivity and astronomy is mainly section 3. So section 1, 2, 3 are paper 1. Akra, yeah. Just look at the specification. I think that's the easiest thing to find out. Yeah. If you just find the PDF of the spec online, and if you're not sure about any of those things, just put Control F on the PDF and just write the word. And if it comes up, and you can clearly see where it is. Thank you, Jaturna. Thank you, Ayan. I'm seeing the answers. Good. Good. Thank you. About 40 seconds left, guys. Thank you. All right, guys. Let's do this one. Right, time's up. Let's have a look. A roller coaster car, I'm going to just make it a little smaller, guys, here. And its passengers have a combined mass of 850 kilograms. Okay, so we know the mass of this one. At the top of the first drop, the car is traveling at 2 meters per second. Now, we just need to imagine this one, guys, right? Let's just draw a small diagram. Let's say at the top here, this is traveling at 2 meters per second, okay? Then at the bottom of the drop, the car is traveling at 28. Okay, so it goes here and is now going at 28 meters per second. Cool, right? Makes sense. Calculate the kinetic energy of the car and passengers at the bottom of the drop. Now, guys, that's really easy. Kinetic energy is equal to half mv squared, which is half times 850 multiplied by 28 squared. So let's use the calculator. Half times 850 times 28 squared gives me 333,200 joules. Thank you. I got the same answer from Arkadas and Jaturna and Nayan. All of you. Well done. Well done. Calculate the change in kinetic energy of the car between the top and the bottom of the drop. Okay, right. So what's the kinetic energy here, guys? So here the kinetic energy is also half mv squared, but m is the same, but v is different to 2 squared. Let's do that. 0.5 times 850 times by 2 squared. Put it in the calculator. I get 1,700 joules. So the question is the change in kinetic energy. So what do? 333,200 take away 1,700. Let's do that. $331,500, guys. Thank you. Where else? Yeah, I see low answer. Okay, good. Thank you, Tiara. Right, that is the answer. Next one. The height of the drop is 38 meters. Okay, the question now says the drop here is 38 meters. Okay. A student says the change in kinetic energy should equal to the loss in gravitational potential energy. Calculate the expected loss in GPE and use the answer to explain why the student's statement is not fully correct. Now, guys, the student says the change in kinetic energy should be equal to the loss in gravitational potential energy. Right. So the student thinks, let's calculate loss of GPE. The loss of GPE is mgh. We know the mass as 850. G is 10. Height is 38. Let's do that. 850 times by 10 times by 38 gives you 323,000 joules. Okay. Now, loss of GPE is 323,000 joules. But what is the gain in kinetic energy? The gain in kinetic energy is 331,000. So that is more than the loss of GPE. So there's loss of GPE, but the car has gained more than that. So possibly, why is that? Maybe there was an external force giving energy to the car. Yes, Chaturma, you can talk about the air resistance and other forces as well. Also, the other thing you can say is there must be an external force giving this extra energy to the car, which is why it was supposed to, if it was purely GPE, it would get a maximum of 323, but it actually got 331, so more than that. So the student answer is not right because there could be an external force. Also, work is done against air resistance, definitely in a car situation and all that. Yeah. After the ride, the brakes bring the car to a stop from 28. Okay, all right. The external force, Tiara, could be the accelerating force. Like this is a roller coaster. So the roller coasters usually have like this rail, and then they're going on it, and then they're being pulled by the external force, right? Like, like if you go on that, right? The acceleration force from outside. Yeah, something like that. Yeah. Now, in reality, like there are certain roller coasters, right? I remember like sometimes they just there are moving wheels that they will move it up to a certain point, and then sometimes they let it have a free run from this high point to the low point. Some of them even accelerate in that part. So this must be doing something like that, right? No. You don't need to. You can just say external force. Yeah, it could be electricity, anything. Yeah, that's right. So the brakes during the car stop 28. The braking force is 12,000 newtons. Calculate the distance required to stop the car. Right, guys. Now here, there are two ways of doing this. The easiest way is the kinetic energy lost is equal to work done. Because work is done by this external force until the all of this kinetic energy comes to 0. So kinetic energy lost is half, m is 850, and the velocity is 28 squared. Okay, is equal to work done is force times distance. But look, we know the force as 12,000 newtons. So I'm going to write 12,000 times d. So what do I need to do? I need to put 0.5 times 850 times 28 squared. That should be divided by 12,000. And that gives me the distance that it travels before it stops is 27.8, 27.76. No, 27 yeah, let's call it 8, yeah, meters. Done. Thumbs up if you understand this. It's a slightly hard one, guys, this last part. It can be also done using, part D again. Yeah, so basically what you need to do here is the kinetic energy of the roller coaster car is converted is used by the braking force. So work done by the braking force is equal to kinetic energy. So kinetic energy is half mv squared. Work done is fd, and you just divide it. Yeah. The braking force is just the force applied by the outside or the braking calipers or something to stop the car. Yeah. I will explain one of you asked about the braking and stopping distance. I will do that. Any other questions, guys, about anything about this one? Anyone? No. Good. Okay. So one of you asked about this braking distance situation. So let me explain this one. I think I might have a really like one of my diagrams. If I can just quickly bring that up. Give me a second. I'll quickly see if I can get it. Yes, I have it. These are from my normal teaching lessons, teaching notes, but this is helpful, right? That's the wrong one. Here. Now, say a driver is driving along a straight horizontal road, and at this point, the driver sees there is an obstacle, say a fallen tree ahead of the driver. Now, can the driver press the brakes like on that spot exactly? Not really, right? Let's say the car was traveling at 20 meters per second. The driver sees the obstacle, figures out if I go at that speed, I'm going to hit it. Not good. I have to stop the car. Then you access the memory and see what should I do. Then it says take your leg off the accelerator, and the middle one is the brake pedal, or the one to the left is the brake pedal if it's an automatic. Just press on it, and then you stop. All of that will take probably about 0.7 seconds in a driving situation in a healthy individual, 0.5 to 1 second, something like that. So in that time, do you think the car is going to just wait until you decide all that? Car is just going to move anyway, right? So car will move, and we call that the thinking distance. So the distance traveled by the car during the driver's reaction time. Then the driver applies the brakes here, but you can't stop the car just like that on the spot. So what will happen now? The car will reduce the speed, it'll slow down and slow down and slow down and slow down and comes to a stop there. Right. Now, when that happens, we call this green arrow distance the braking distance. So, what's the total stopping distance then, guys? It is the sum of thinking plus braking distance. That's really the basic idea here. Thumbs up if you understand it, or say yes. So, just tell me a letter Y or something in the chat if you understood it. Just letter Y will do. And if you have any questions about it, please ask me. Anyone? No? Great. Just directly related to this, you need to know about factors affecting this thinking and braking distance. So let me quickly show you that as well while we are here. So here you can see thinking distance. Now listen, people get these things a little confused sometimes, right? So be very careful here. Thinking distance is all about the driver. Why? Because if I'm driving a car, I have to take the leg off the accelerator and press on the brake pedal. Thank you, Nikhil. Right? Press on the brake pedal. So that is up to me, right? Right? So the thinking distance is directly related to the person who is driving. So the factors affecting alcohol. If a person is under the influence of alcohol or drugs, now when you say drugs, it's not necessarily like the recreational drugs. It could also be prescription drugs. There are certain drugs that can make you drowsy, right? Certain like they can make you a little sedative, right? So if you are under the influence of certain drugs or alcohol, or if you are tired, I'm sure you've seen along the motorways, they show you like tiredness can kill, take a break. So that one, right? Or poor visibility. Now let's say you're driving in a lot of rain, or there's a lot of like a snow or hail or something like that, and then you're trying to see, oh, is that a tree, or is there something wrong with that, or is that car not moving? It's hard to decide. So what will happen? It will be harder because of the poor visibility. Distractions. So you have very loud music in the car, you have friends in the car, maybe children in the car, things like that can affect the thinking distance. Also the age. If someone is older, it will be the person can be a little slow. I mean, it's just a general thing. If you think about it, say if a person is 75 years old compared to that same person when he or she was 25, obviously the 75-year-old version is a bit slower. That's natural, right? Speed of the car as well. If you're traveling faster, if you're going at 70 miles per hour in a motorway, then it's going to take longer. So all of these things are the factors affecting thinking distance. What about the braking distance? Now, the braking distance is all about the car and outside conditions. So after I press the brake pedal, the rest is not, I cannot really control it, right, as the driver. Condition of the road, ice, water, oil spills, things like that. Condition of the tires, condition of the brake pads. If they're worn out, it's going to take longer. Mass of the car. Now think about this, guys. Say you're traveling in a car, and it has you're at a certain speed. Imagine you're traveling at the same speed in a truck, and if you apply brakes at the same time, you'll be able to stop the car quickly, not the truck. Why? Because it has greater mass. Also the speed. So I highlighted his speed here because that is in both. If you want to take a screenshot, guys, by all means, please take one. Any questions? Tell me Y or N, yes or no. Please respond so I know. Thank you, guys. You could get these questions in your GCSEs a lot, and I've seen them multiple times in your Edexcel papers. Good, Ayan, thank you. Aktas, thank you. Any questions? Tiara, no problem. Happy to help. Happy to help, right? Okay, cool. Take a screenshot. Right. So let's try another question now. See, what we are doing is we are doing a mixture of like theory and questions. And question time. Here's another one. really like interesting question. These skydiver questions are like very popular, guys. Let's try this one. So here's the question, parts A to D. Right, I'm going to give you about I think this might require about 4 minutes because of the length of the question and looking at this. Okay, that's okay. We'll run this timer. Just trying to. I'll leave it like that for now. Right, let's do this. Mukesh, do we have to draw ray diagrams in our exam? Ray diagrams is optics, which is in mainly in wave section. So section 2, yeah. So this is mainly paper 1 stuff. Skydiver questions, they're like really popular. Like I've seen them multiple times. Right. Okay. That's okay. All right. I will. You will see the rest of it on the channel. No, Azim. This is Edexcel mainly. I'm running an AQA specific one tomorrow. Tomorrow, UK time, 5 to 7 p.m. Yeah. So if you want to come, or if you want to just share the link with any of your friends, anybody can come. Really, I'm just running it for free for anyone. No problem. 2 more minutes to go, guys. Think about this. Yeah, we can do that. I mean, this question could be both Edexcel and AQA, by the way, right? Because in AQA, this is topic 5, forces and motion. Yeah, but I will be doing a separate one for AQA tomorrow. So if that's your exam board, you could do that one. Yeah. Be very careful about the forces in these type of questions. And even though the question does not ask to draw the diagram, draw a simple diagram, in most physics questions, doing so will be really useful, because when you draw it, it's very easy to understand. No problem, Les. Yeah, I'll see you tomorrow at 5 p.m. The AQA version. Yeah. You will have an equation sheet, Azim. Yes. There is an equation sheet. Yeah. Yeah, no problem. Thank you, Les. About 45 seconds to go, guys. Guys, where are you guys from? Message me which part of. I believe most of you guys could be from UK, or where are you from? Where are you, like which city, or what's the closest big city? Just out of curiosity. Some of you are my students, I know, like those are from my classes, but I've seen some of the names. Brighton, all right, that's nice. Yeah. No problem, Azim. Yeah, Middlesbrough. Good. See you. Yeah, it's 5 to 7 tomorrow, right? Not the same time as today. Tomorrow is 5 o'clock. Yeah. Right, time's up, guys. Let's have a look, shall we? I'm going to make this a little smaller so I have some space to do the working out. Yeah. Calculate a skydiver of mass 75 kilograms jumps from an aircraft. Hatfield. Okay, Hatfield is quite close to me actually. I'm in Buckinghamshire, Aylesbury. So it's about 45 minutes an hour, something like that. I used to work in a school in Harrow for 7 years, which is kind of close to Hatfield. Right? Birmingham. Good. Right. Calculate the weight of the skydiver. Now, guys, weight is mg. M is 75. G is 10. So the answer is 750 newtons. Easy. At one point during the fall, the air resistance is 520. Okay. So we have the skydiver, and the downward force is 750 newtons. And the question says the upward air resistance is always opposite the motion, is 520 newtons. Calculate the resultant force on the skydiver. Resultant force is 750 take away 520, which is 230. Yes, Mukesh, thank you. 230 newtons. Okay, if I write like that, what am I missing? I'm not going to get 2 marks if I do this. What am I missing? Somebody tell me. In the chat, go on. If I write this, I'm missing something. There's one thing I'm missing here. The direction. Thank you, Tiara. So I should say downwards. I can draw an arrow, or within brackets, I can write downwards. I have to say the direction to get both marks. Really important. Thank you, Jaturna. Yes. Next one. Calculate the acceleration of the skydiver at this point. Okay. Now, for part II, for the acceleration, I write the formula F is equal to ma, and F is the resultant force, which is 230. M is 75. A. Oh, that's really easy. What do I need to do? 230 divided by 75 gives me 3.06 recurring. So acceleration is 3 point. Yeah, divide. Did I say times? Sorry if I said. I did division on my calculator, and that's what I meant to say anyway. So 3.06 recurring. So let's call it 3.07 meters per second squared. That's also downwards. For this one, direction is not compulsory, but I'd rather do. Okay. The person is accelerating downwards at 3.07 meters per second squared. The skydiver reaches the terminal velocity, state the resultant force, and explain, using Newton's laws, why the skydive is no longer accelerating. Beautiful question, guys. We've seen this multiple times. This one, yeah. So let me just type this up because of the time. So when you get a question like that, always look into what the question is really asking, right? I'm just going to change the color. Okay. State the resultant force at terminal velocity. The resultant force is 0. Right, that's the first part. So I just answered that one. Explain using Newton's laws why the guy is not accelerating. Okay, so at this point, the weight of the skydiver is equal to the drag. Now, there is an upthrust as well. Yeah, I'm going to explain it here, right? There is an upthrust as well, but that is not really significant. So let's not worry about that one. At this point, the weight of the skydive is equal to the drag, and the resultant force is 0, right? According to Newton's second law, F equals ma, when F is equal to 0, acceleration is 0. So that's why the skydiver is no longer accelerating. Yeah? Thumbs up if you understand it. Thumbs up or any sort of, yeah, thank you. What is the resultant force at terminal velocity? Why? Yeah, okay, yeah, that's it, right? So the resultant force using Newton's laws, why the skydiver is no longer accelerating, the resultant force is 0. Downward force and upward force are equal and opposite. Done. The skydiver lands on soft ground. Okay, that's the last part. Yeah, let's have a look at this one. The skydiver lands on soft ground, coming to rest. Okay, which means final velocity is 0 from 5 meters per second, that is initial velocity, in 0.8 seconds. That is the time. Calculate the force exerted on the skydiver by the ground. Again, this can be done in two different ways, but I'm just going to do the obvious one first. Remember the formula A is equal to V minus U over T, guys, right? V is 0, right? U is 5. Remember, why is V 0? Because the person lands on the soft ground and stops eventually. So final is 0. Initial is 5 divided by the time is 0.8. So all you need to do is 5 divided by 0.8. You get a negative sign here because it's in the opposite direction, guys. You don't need to worry about it. It's 6.25 meters per second squared. Now that is my D. Right. If that's your D, what's the force now? Sorry, that's your A. If that's your A, what is the force? Oh, that's really easy. F is equal to ma. The mass is 75 kilograms. We just know that from the beginning, multiplied by 6.25. So times by 75 beautifully gives me the answer 468.75 newtons. Done and dusted. You got this right. That is a hard one, guys. This is a hard one. Yeah? Give me some sort of some time if you understand it. Do you understand it? Thumbs up or some sort of yeah, well done, well done. Good, thank you. Great, that is a good question, guys. Slightly tricky one as well. So I'm just going to clear the board now. So we've discussed about these things. We discussed about forces and their effect and stuff like that. Electricity is a very interesting question. So let's try with an electricity question. So here is your first electricity question, guys. I'm going to start with a relatively easy one. Okay, everybody? I'm going to run 2 minutes, a timer for 2 minutes, guys, for this one. And let's do it. Electricity. Please send me the answers. Yeah, of course, yeah. I'll know you can watch if you are AQA, that's fine. But also, I'm doing an AQA specific one tomorrow, Sunday from 5 to 7 p.m. UK time. So if you want, you can come to both. If you want, you can come tomorrow. I'm not doing exactly the same question. I'm doing different stuff with them. Yes, Demola, you can ask me if you have a question. I'm always watching the chat, so just let me know. Let me know in the chat and I will answer. Yeah, that's okay. I'll know it's tomorrow at 5 p.m. Demola, you can message me the question you have. Yeah. No, they won't ask you questions like how long does it take and stuff like that. No, they're more like practical sides of it. No, that unless they've given the information to do some sort of a calculation. Say, if they've given you the no, that is, you know what? Because there is varying acceleration there, you will not get those calculations, right? If they mention, okay, assume this acceleration to be constant, and they give you some sort of a value, that's the way if they want to do it, they can do it. But I doubt it. Thank you, guys. You're sending me the answer. Okay, Les, I got the answer. Ayan, I got the answer. Thank you for that, guys. Anyone else? Just send me the answer, quick, please. Thank you. Thank you for part B's answer. Good, good. All right, guys, time's up. Let's have a look. A bulb has a resistance of 15 ohms. Okay, this is R. The current through it is 0.54 amps. Calculate the potential difference across the bulb. Okay, so I know the current and resistance. Obviously, V is equal to IR. So I here is 0.4, R is 15. That's going to give you, I think, 6 volts. Yeah, 15 times 4 is 60. So 0.4 times 15 gives you 6 volts. Calculate the power of the bulb. Now, guys, the formula for power is IV. I'll tell you a way to memorize it. Some people think of this like an ivy leaf, as an ivy leaf, like the plant, poison ivy or ivy. So P equals IV, right? You can use that to memorize it. So the current here is 0.4. We just worked out to be 6, and that is 2.4 watts, capital W. Done. Part C. Thank you, guys. Yes, Tara, you got it right. The bulb is left on for 5 minutes. Calculate the energy transferred. Now, energy transferred is power times time. Why is that? Remember the formula we discussed earlier, like in the first slide? Power equals energy divided by time, right? Now, energy is power times time. Okay. Power is 2.4 time. 5 minutes. Now, look, you can't put minutes. You have to get it into seconds. So that will be 5 times 60. So all we need to do is 2.4 multiplied by 5 times 60. And that gives you the answer as 720 joules. Done and dusted. Well done, Tiara. And right, good. Any questions? Well done, Ayan, for the power. And yeah, good. Any questions, guys? Anybody? If you have any doubts, questions, anything, just let me know. No, I'll take that as a no. That's good. Right. Guys, for electricity, it's really important that you properly understand the difference between series and parallel circuits. Now, this is a really interesting one, and you get loads of questions on the difference between series and parallel. I can quickly probably show you this. One second. Right, here is a proper comparison between series and parallel circuits. Sorry, the bottom bit here is covered. I'll explain that to you. So, in a series circuit, all the components are placed side one after the other. So look at it. You have this first resistor, the second one, third one, like that. But in a parallel circuit, they are placed side by side. Look, this one creating another parallel branch, it creates another parallel branch like that. In series circuit, there is only one path for the current to flow. See, there is only one path. Current will go like that. In parallel circuits, there are multiple paths. It can go like this or this or this. Here, in a series circuit, current through each component is the same. Look at it. 2, 2, 2, 2, 2, 2. What about this one? 5 amps come here, and it goes 2 that way, 1 and 3, 5 take away 2, 3 down here, 1 go that way, 2 amps, all that. So that is splitting up. The voltage splits up. Look, the 10 volts is split up as 3 and 5 and 2. Whereas here, if this is 6 volts, all of them have the same voltage, 666. So if a fault develops in one component, all others will not work. Now think about it. If this resistor got damaged, there was only one path and that is gone. Now what happens? It will not work. Whereas here, if the top path is damaged, well, there will be no current in that, but the other two will still work. That's that one. Then, all components are controlled by one switch altogether. So if you put a switch anywhere in this first circuit, it will control everything together. Everything is on or everything is off. Whereas here, I can put a switch here to control that one. I can put a switch here to control the second one. Or I can put a switch here to control the third one. Or I can put a switch next to the power supply to control everything all together. So you have more control there. Examples of series circuit would be Christmas lights. If you think about the lights that you see on, in Oxford Street in Christmas time, like that. And parallel circuit, probably like house wiring and car wiring. House wiring and car wiring are both a little complicated, but it has more parallel features. Right. That was just a quick recap of the circuit stuff, everybody. Let's do another electricity question. This question is about, again, circuit stuff. Really good question. Electricity. Right. In a bit, we are just going to go to more, not yet, I mean, in a bit, actually, we are going to go to more triple only content. So if anybody has any particular thing that you'd like to work on, if you are combined, especially if you are doing combined science, and if there is anything you need help on, just let me know. Right? You just need to let me know in the chat. I can talk it through. So let's spend about 2 minutes to try to do this question, guys. Please make sure that you draw a simple diagram. That's necessary. And send me the answers when you have it, guys. Yeah. Part A, B, C, D, E. There are 5 parts. Send me the answer when you have it. Just over a minute left, guys, now. There are formulae that you can use to calculate the total resistance. I know some people learn this at school or with your teachers or something, but you don't really need that for these questions. You can do it without that. But you can do it with that or without that because that's not in the spec. So there's an alternate way of doing it, simple way. 5 seconds. Right, that's enough time, guys. Let's have a look. A series circuit has a 24-volt battery and 2 resistors, 4 and 8. Okay, let's draw the circuit. We have a 24-volt battery and 4 ohms here, 8 ohms here. Okay, calculate the total resistance. Now, this is really easy, guys. The total resistance is the sum when they are in series. 8 and 4, 12 ohms. Thank you, Tiara. Thank you, Coffee with Tina. Thank you, Ayan. Okay. Calculate the current in the circuit. So V is equal to IR. The voltage provided is 24. Current you don't know. The total resistance is 12. Obviously, I is 2 amps. Thank you. Calculate the potential difference across the 8 ohm resistor. So what is the potential difference here? Now we can use V is equal to IR for this component. So my V, I don't know. I is 2 because remember, in a series circuit, there is the same current goes through this, through that, through this, and back here. So at any point, it's 2 times by 8. The answer is 16 volts. Well done, well done. I got the answers already. Coffee with Tina and Ayan and Tiara. Good, good. Right. The next one. The two resistors are now connected in parallel with the same 24-volt battery. Right. Let's do a new diagram, shall we? So, same two resistors, but these are now connected in parallel. So I'm just going to do the same power supply, so 24 volts. And this one here is 4 ohms, and this one here is 8 ohms. Okay. Calculate the current through each resistor. Now, remember in a parallel circuit, all the resistors have the same voltage. Okay. If that's 24 volts, we have 24 volts across both. So, for this one, I'm going to write V is equal to IR. The voltage is 24. I don't know the current. R is 4. Okay. So you divide both sides by 4. Obviously, current here is 6 amps. Right. Now, we know the current here is 6 amps. I can do exactly the same thing here for the second one. Current here is voltage 24 divided by 8, which is the resistance here, so 3 amps. Now guys, look at this. We have 6 amp in the yellow branch, and we have 3 amps here in the blue branch. I'm just color coding it. Now, where did we get these two currents? It started from this top one here. This particular question is not asking for that value, but do you understand the current in the main branch should be 6 and 3, 9? You don't, the question is not asking it, but send me a letter why if you understand it. Yeah? Right. Next one. State the advantage of connecting devices in parallel in a home. Right. So, when they are connected in parallel, you can control each component separately. Right? Which one, Tiara, do you want me to explain? This one here. So, we have 24 volts across both, part B, yeah? So, if the voltage is 24, current, I don't know. The resistance here is 4. So, what do? 24 divided by 4, 6. So, that one is 6 amps. Current through each resistor. First one is 6. Similarly, 24 is a voltage still. Divided by 8 gives me 3. Yeah? So, that's it. Then I just said the current in this branch at the top is the sum of 6 and 3, 9. But the question isn't really asking it. State one advantage of connecting devices in parallel in home. So we can say components can be controlled separately. Yeah. Because otherwise you don't want to turn the switch in your kitchen and all of the other lights to come up, right? That's not going to be very helpful at home. So you need to be able to separate them in a home. One thing is it can be controlled separately. Also, if a fault develops in one, if a fault develops in one component, others will still work in parallel. Right, that's it. So those are some advantages of using parallel circuitry. Done. Right. I think that's quite sufficient. Let's do another one. These are all possible questions, guys. Right. Specific heat capacity is a very popular question you get. Let's try a question on this. Does anybody want me to explain the theory of the specific heat capacity, guys? Anyone? Or you're okay to just do the question? Let me know in the chat, please. I'm watching the chat now. If anybody wants me to explain it, theory, just say T for theory or Q for question. T for theory, explanation, Q for just the question. Yeah, okay. Let's have a look. Right, guys. Now, here's the idea behind specific heat capacity. Look at this one. Say, this is not the exact practical, by the way. I'm just, this is a different one, right? So you have a container, and inside this you have 1 kilogram of water at 20 degrees Celsius. And you put a heater and you connect it to a joule meter, and there's a temperature probe connected to a data logger to a computer. Now, you provide energy and you see the amount of energy needed to increase this temperature from, say, it starts from 20 to go just 1 up. Now, when you do that, experimentally, you will get close to 4,200 joules. So here's where the definition of that comes from. The amount of energy needed to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. Therefore, specific heat capacity of water is 4,200. Look at the units, guys. Joules per kilogram degree Celsius. Does that make sense, everyone? Let's have a look. Units of specific heat capacity. Specific heat capacity is joules per kilogram degree Celsius. Right. Now, let's have a look at this question. Yes, Clipora, I will go to magnetism in a bit. Yeah, after this question. Yeah. Right, everybody, let's try this question. Clipora, are you combined or triple? Message me in the chat. Combine or triple? Right, everybody, let's try this question. I'm going to run the timer again. Probably. Right. Hi, Nayonika. Right. I will explain specific heat capacity, and this is specific heat capacity. Let's do specific latent heat after this, okay? So I'm going to run the timer for 2 minutes, everybody. Let's do that. Combine, yeah. No, Sunster, this is Edexcel. So I'm running this session today for Edexcel for another until about 9 o'clock-ish. And later, tomorrow, 5 to 7 p.m., I'm running one for AQA. So if you are AQA, I'll be running more AQA specific one tomorrow. Yeah. And this particular one in AQA, it's in paper 1, because it's energy. It comes under energy topic, and the specific heat capacity, latent heat, comes in the other one. That's okay. Yeah, I'll be doing some magnetism in a bit, Sunster, which is also in your uh, yeah, yeah, gas GASGJO. Yeah, yeah, that's okay. Yeah, combine Edexcel. Uh, yeah. I'm going to do this one when you're in about a minute. Everybody, try this. Do this on your own. And remember, in the exam, you always need to try to answer all the questions. Like I've seen some students just leave the questions because they are not sure. Uh, well, try to do it to the best of your ability. But if that doesn't work, then even if it is a guess, that is still helpful. Because when you do that, because if you leave it blank, it's going to be zero, right? Yeah. Clipera combine higher. Are you asking about AQA or Edexcel? Edexcel, right? I had this image. I'm going to show it on the board at the beginning. If I would personally work on these topics, guys, I had this at the beginning, so some of you may not be, maybe you guys weren't here. So if you are combine everything in those black boxes, and if you are triple, everything, including the green box. Yeah, Clipper, take a screenshot. Right. Let's look at the question, guys. Right. I'm just going to make this a little small so I have more space now. A 2 kilogram block of aluminium is heated using an electric heater. The temperature rises from 20 to 95. That gives me my delta theta. The specific heat capacity of aluminium C is this much. Calculate the energy needed to heat the block. Oh, that's really easy. E is equal to mc delta theta. M is 2. C is 900. Delta theta is 95. Take away 20. You can put like that, or you can just put 75. Same thing. So 2 times 900 times 75. Just going to put in the calculator. I get 135,000 joules. Thumbs up if you got this. Thumbs up, or any reaction really. 135,000 joules, guys. Thank you, Nayonika. Okay, good. The heater has a power of 60 watts. Calculate the time taken to heat the block. Okay. Now, energy, power is equal to energy divided by time. We know the power as 60 watts. Energy is 135,000 divided by time. Obviously, time is, you need to move it to that side, 135,000 divided by 60. And that gives you 2,250 seconds, guys. Remember, this is in seconds, okay? The time taken is 2,250 seconds. If you want to get it into minutes, it's 37.5 minutes. In practice, the experiment takes longer than calculators suggest. Why? Because energy is lost to the surroundings, right? Energy is lost to the surroundings. So the total amount of energy supplied will not be absorbed by the aluminium block. Therefore, it will take more than that. Water has a specific heat capacity of 4,200 joules per kilogram degree Celsius. Explain why water is more suitable than aluminium as a coolant in a car engine. Now, water has a higher specific heat capacity. Now, when the specific heat capacity is high, it can absorb lot of energy, but will not increase the temperature as much. Let's write this one. Water has a higher specific heat capacity compared to aluminium. So it is difficult to heat up water. So it can absorb heat and change the temperature by a small amount compared to the same mass of aluminum. See, if you have 10 kilograms of aluminum and 10 kilograms of water, water can take a lot of energy before it goes up 1 degree, whereas aluminum will heat up quickly. Yeah? Water is a better coolant, it can absorb more energy, not be, yeah, that's right. Like same thing here in different words. Yeah, I need to check the time stamping. I'll do that, but the video will go to the channel, then I'll try and time stamp it by questions. Yeah, that's it, guys. Right, any questions? Anyone? No. Right, now let's go to another question on magnetism. Guys, these are still not, I know I was supposed to go to triple only content a little bit earlier, but because of the way the questions kind of worked out, I'm still in this one. Right. All right. Let's try this question. Now, this is about the magnetic fields. If you are still combined, guys, this is for everybody, right? Good. Can you send me the word triple or just TR if you are triple science? I'd like to know. Just to see like who needs like only triple content, triple only content. Just put TR if you are triple only. Thank you. 1, 2. Thank you, Sophia. Okay, so I'll be doing more. Thank you, Jaturna. Okay, Les, thank you. This is still combined and triple both, yeah? Samir, thank you, Samir. I didn't start the timer for this one. So, 2 minutes again, guys. I will definitely go do the triple only content as well in a bit, guys. A couple of questions, but I'd like to finish these as well because these things can come up in both combined and triple. Yeah. Let's start this. Magnetic fields is a big part of this paper because you get a lot of questions like all the time. A lot of you are triple, I can see. If you are combined, just put the word C, just letter C. Go on, guys. Send me the letter C if you are doing Edexcel combined science and you have your exam on Monday. Thank you. About 55 seconds. Yeah, that's okay. Yeah, I'll be doing more of those tomorrow, less. And magnetic fields is for you guys. It's also in paper too. So this is there. Thank you. About 30 seconds, guys, and then I'll go through this question. If you want me to explain any theory parts in any topic, really, let me know in the chat, because magnetic fields is one of those things where you need any things. Yeah, it's quite difficult to exactly predict things, Ian, here. As in, like for maths, I did it, and then there were like a lot of like successful predictions. I think there were about 12 questions in the last paper. That's because in maths, you have the same content, three papers. Paper one, once we've seen that, we know what came in that. Paper two, we can reduce the pool, and paper three. This is quite difficult to predict like that. There are stuff that you get pretty much every year. So so just you just need to know all of them, really. And these are like the most common exam questions that I can tell. I spent some time earlier today just to extract these topics, so they are more common. I can tell you that. Right. And one of the things, guys, another really good thing about Edexcel, yeah, when COVID hit, schools were closed and people could not do the practicals, the core practicals. Now, other exam boards didn't do this, as far as I am aware, but Edexcel did these core practicals, like Pearson. Under the Pearson, they did their core practicals. So they are there. If you go to YouTube and you just put like, or the practical, just put like Edexcel GCSE Physics practicals, they all come up. So I would definitely recommend that you watch them, because they are directed from Edexcel. They are very reliable. They are correct. They're all good. I use this in my lessons, and I kind of direct my students to them because they come from the exam board. So please do that. A current carrying wire is placed at right angles to a magnetic field. The magnetic flux density B is 0.05 Tesla. The current is 3 amps I, and the length of the wire is this. Oh, calculate the force on the wire. Now, guys, the formula is F is equal to BIL. Bill, some people call it, right? 0.05 times by I. The current is 3, and the length is 0.2. So all you need to do is 0.05 multiplied by 3 multiplied by 0.2. I got 0.03 newtons. Who got this? Thumbs up, or do some reaction if you got it, or send me Y for yes in the chat. If you got 0.03 for the first one, yeah, good. State the rule used to find the direction of the force. That is Fleming's left-hand rule. Because it's one mark and it's just to state the rule, that's okay. So Fleming's left-hand rule is basically FBI. FBI. Force, F. B is the symbol for field, magnetic field. I for current. So what the Fleming's left-hand rule says is, when the first three fingers of your left hand are held perpendicular to each other, such that your first finger is in the direction of the magnetic field and the second finger is in the direction of the current, your thumb shows the direction of the magnetic force, FBI. Okay. The current is doubled. State the effect on force. Okay. Now, we know the formula is F is equal to BIL. As long as L and B remain constant, F is proportional to I. Oh, if the current is doubled, what will happen to the force? It will double too. Force will double. Thank you, Clipora. Yes, that is the correct answer. All right. Part D. Explain how an electric motor uses this effect to produce continuous rotation. Right, 3 marks. Now, guys, if you think about an electric motor, the very simple arrangement, we have something like this. We have a magnetic north pole here, south pole here, and the magnetic field between those two is like this. Now, here we have slip rings, right? And then this is carbon brushes here, and then connected to a power supply, DC supply. Now, current goes through this one that way, and then current comes through it this way. Now, think about the left-hand side one here, FBI. Now, B is this way, right? Because it's from north to south. I is that way. Oh, the force is down. Downwards. Think about this one, FBI. So it will be the exact opposite, right? So BI and XF. It's a bit crooked, guys. Let me just correct it like that. So what will happen? This thing will rotate like that. Now, what is the point of this split ring commutator? The split ring commutator, at every half turn, it switches the contacts. Now, why is this necessary? Because otherwise, so imagine what happens in one half turn, right? If you imagine you just don't connect it like this, if you just have it like this, it rotates because there is an anti-clockwise moment, right? There's a force. Now imagine this is my calculator is a coil. I have a force acting upwards on this side. I have a force acting downwards. Sorry, I'll do the same thing as the board. Downwards on this side and upward on this side. So what will happen? It will rotate, right? It will rotate like that. Understood? Yeah, slip ring commutator dynamic, I'm going to do that now, right? Now, the whole point of slip ring commutator, guys, imagine if you didn't have that. What will happen is these two, after one half turn, it would look like this. Are you with me? After one half turn, it would look like this. Thumbs up if you, oh yes, if you understand it. The slip ring, if there was no slip ring commutator, and if it was just rigidly connected, it will go like that. Now the problem is, right? The problem is, if it goes like that, it's not less. What happens is, right? Let me just see if I can just get a wire to explain this one. So you have a wire, you have connected it like that. So if I turn it half, wouldn't it go like that? Yeah, I'm going to explain it here, right? I'll explain, right? It goes like that, right? Now, if I connect these two rigidly, and even if I manage to move it, what will happen? This will all get twisted up, right? It's not going to work, is it? Right? So what we need instead is to use a slip ring commutator, and it flips the direction every half turn. So what happens is this is free to move, and this doesn't happen. Also, there's another side to it. When, let's say if this happens, now look at the direction. The direction now is like that because this wire gives current this way and this goes that way. So the wire, when the current is going that way, the force is down and that is up. Oh, that's the opposite. So if you don't switch the direction at the correct time, what will happen is rather than going it continually, it will just flip back and forth like that. That's not really a motor, is it? Thumbs up if you understand it, right? If you don't use a split ring commutator, it will not rotate in a continuous direction. It will go like that instead. So what we do is we have the split ring commutator. Every half turn, it will change the direction. It will change the contacts, right? Now, how do we write it? Let's see. That is the setup here. Explain how an electric motor uses this effect to produce continuous rotation. Let me write a GCSE exam standard answer to this part. when a current passes through the wire, there will be an upward force on one side of the coil and a downward force on the other side due to motor effect. So the coil will rotate. Continuous rotation part, there are slip ring commutators. Sorry, not slip ring, split ring, my bad. Split ring commutators that change that switches the contacts each half turn to make sure that the coil rotates continually in the same direction. Tara, is that okay now? Do you understand? Guys, thumbs up if you understand how I did it and what to write in the exam. That's how you word it. Yeah, I know understanding it and writing it is kind of different. So there you go. So if you want to take a screenshot, guys, please go ahead and do that. And that's it, really. Right. Guys, I'm just going to do this one, and possibly after that, I'll just kind of go to more triple only kind of content. Right, Ayan. Split ring and slip ring. Now, slip rings are, listen, as the word implies, split rings are rings like this. And these are found in motors as well as dynamos. Slip rings are found in alternators. So here you have it's quite difficult to draw this, right? A full ring, and this wire is in contact with it. The other one goes through it, and there is a different ring here, and the second one is in contact with that. Now here what happens is the whole thing is in contact with the like this ring is always in contact with this wire. This ring is always in contact with this wire. So it slips on it, hence the word slip ring. This one is split into two parts. So this is a split ring commutator. These are slip rings. Slip rings. I know they sound quite similar. People get confused by that. So split ring commutator and slip rings. Thumbs up if you understand it. Yeah? Thumbs up, thumbs up. Is all good? Give me some sort of a... Yeah? Good. Right. Let's go to another one, guys. So these are the things that I think you need to work on, right? Right. Let's do a question on transformers. Now, transformers are also very... slip rings are in alternators, yes. Split rings are found in motors and also in dynamos. The difference between dynamo an alternator is that alternator provides an alternate power supply, right? The it generates alternating voltage, whereas the dynamo produces direct. Right, guys. Here's a question about transformers. Uh, let's have a look. I think probably about 2 minutes again. Let's do this one, guys. Everybody. 4 different parts. Let's try this. Any theory parts or questions you can ask me, like the one I did earlier. Thank you, guys. Yes, Les, what do you want me to do about? Yeah. Noyonika, I'll show you the equations in a bit. Yeah, I have them. I have the. I showed them earlier at the beginning. I think probably some of you weren't here. Maybe I will definitely show you in a bit. Yeah, towards the end, I will show that. Or are you referring to like the equations of this one? You're probably asking about n primary divided by n secondary is V primary divided by V secondary. Also for power, n primary divided by n secondary is V second. N primary divided by n secondary is hang on, sorry. VP, IP, VS, IS. So V primary divided by V secondary is I secondary divided by I primary. I'll write it on the board in a bit. Yeah. Good, good, good. Right, time's up, guys. Let's have a look. A step up transformer has 500 turns in the primary coil. Okay, so I know this is in primary. And 3000 turns in the secondary coil in secondary. The primary voltage V primary is 230 volts. Calculate the secondary voltage. So what's the formula? N primary divided by N secondary is V primary over V secondary. Okay. N primary 500. Guys, let me just tell you one thing. Did you notice in all the questions I did today, and I do it all the time, you guys, some of you are my tutees, so you know this one. Did you see how I underline and write what it is? Underline and write what it is. It really helps. It really helps because sometimes now I don't need to look at the whole question again, and because I know I've kind of annotated what I need, and I even wrote what that is. Right? It really helps me because when I see those three, I know the formula. Everything is easier. So make sure you do that. Okay. So 500 divided by 3000 is V primary. The primary voltage is 230 divided by V secondary. Now what do we do? 500 goes into that 6 times. V secondary is actually 230 times 6. So V secondary is 1380. Yeah. 1380 volts. Thumbs up if you got this one, or any emoji, so I know. Good. The primary current is 6 amps. Calculate the secondary current. Assume it is 100% efficient. Now, guys, in a 100% efficient transformer, the power input, remember P equals IV. So V primary, I primary is the same as V secondary, I secondary. Okay. So V primary, what's the V primary? We know 230 multiplied by I primary. The current, primary current is 6, okay, is equal to V secondary. We just worked out to be 1380 times I secondary. I don't know. What do I do now? All I need to do is 230 multiplied by 6 divided by 1380. That gives you 1. Is that what you got, guys? 1 amp? 1 amp? Yeah? Right. Next one. Explain why the national grid transmits electricity at high voltages. Now, guys, remember, power is I squared R. Now, if I use very low, if I use very high currents, the problem is there will be a large amount of power dissipation, right? So what will happen is, actually, I have a video, a separate video exactly on this, guys. If I can quickly bring this out, I think it will be helpful to you. Give me a second. It'll be really quick. Is this question here. So I'll send you the link in the chat, guys. You can just open it to watch this later. Actually, that's the wrong one. That's the wrong one, guys. My bad. Here's the correct one. Sorry. Here's the correct one. Now, I'm just going to show it with this one, with my own video. I'm just going to share my one here, right? So look at the question. The national grid uses very high voltages to transmit electricity over long distances. Explain why a high voltage is more efficient for this. So look at the answer, guys. Right, sorry about the quality of the video. It's not the best. Using a high voltage reduces the current in the transmission because P equals IV. The higher the voltage, the lower the current. Lower current means less energy is lost as heat due to resistance in the wires. This makes the transmission of electricity more efficient. It's not losing a lot of energy during transmission process. Transformers are used to increase the voltage just before transmission and decrease it before use. So we have a step-up transformer near the power plant where you increase it to 400,000 and it is transmitted to where we want to go, and then at the end it's reduced. Take a screenshot. In fact, I've sent you the link, guys. So that is technically the answer for this one. Explain why the national grid transmits electricity at high voltage. According to P equals I squared R, if the current is high, the power dissipation is high, lot of energy is wasted. So to reduce that, we increase the voltage, which decreases the current because the power is constant. Now there is minimum energy loss during the transmission. Is that all right, everyone? Right. Next one. A student says step-up transformers increase the power in a national grid. Okay. Explain why the student is wrong. Now, guys, the power is the product of IV. That is not, that the power doesn't change. So what happens is step-up transformers increase the voltage, but that reduces the current. Now, let's say the power is 1000 watts, for example. When I is 10, V is 100. Now, if I increase V to 500, I is 2. If I increase V to 1000, I is 1. See, the higher the voltage, the lower the current. But what about the product, guys? 500 times 2, 1000. 1 times 1000, 1000. It's always the same. So for last part, this guy thinks the step-up transformers increase the power. No, it does not. It's the power does not change. It's just the increases the voltage. But when you do that, the current decreases. All good, everyone? Right. That one is done. Now, a few things that I said I would show earlier. Here you can see the things that I think are quite common in Edexcel GCSE Physics papers. So please make sure you learn these things. And for combined science, these are the formulae that you need to, the main ones that you need to know. So if you want to take a screenshot, get that, please. And sorry about this, the bit covered from my video. There is kinetic energy, sorry, elastic potential energy is half kx squared is what you can't see. I mean, I can do like that here if you, oh, that's better, I think. EP equals half kx squared. John, for AQA, I'm running the session tomorrow from 5 to 7 p.m. I'll do exact AQA specific. But yeah. Is it the same for step down? Both step up and step down transformers change the voltage. But if in a step down transformer, if you reduce the voltage, the current increases, Tiara. Yeah? Right. The triple only formulae are here. These are the main triple only stuff, guys. Yeah. The power output stays the same, yeah, because it's the IV product. Yeah. But in reality, as the electricity is being transferred, obviously there is some heating taking place and some energy is lost along the way that you can't avoid. Yeah. But for GCSEs, I have not really seen any, even like the transformer questions, they ask you to assume that they are they ask you to assume that they are 100% efficient. So VP IP equals VS IS. Right. Cool. Let's do another one. We are nearly there, guys. Let's just quickly have a look at some of the questions. Right. Let's try this one. This is a moments question. Now, guys, these couple of questions that I'm doing towards the end are triple only, by the way. Yeah? Yeah. Let's try this one. This is just a moment question. Just going to give you again 2 minutes, guys. And we'll give it a try. Principle of moments. You need to know how to define moment as the product of the force and the perpendicular distance from the pivot. Principle of moment says that the sum of clockwise moments is equal to sum of anti-clockwise moments in equilibrium. So when the when there is no when it is in equilibrium, yeah, all that. Give this a try, and I will do this in a bit. Guys, we were supposed to finish at 9. I mean, I was planning to do it like that. I'm okay to do this a little longer and just finish a couple of more AQA style questions. Not AQA, my bad. Triple style questions. If anybody has any particular questions, I can answer them. 40 seconds more, and I will discuss this one, guys. Always draw diagrams. I mean, to this question, and also in generally in physics, guys, it's always good to draw diagrams. All right, guys, thumbs up, time's up. Let's have a look. A seesaw has a pivot at its center. Okay, so just draw the seesaw like this, and it's pivoted at the center, so roughly there. A child of weight 400 Newton sits 1.5 meters to the left of the pivot. Okay, so he is the person. The weight is 400 Newtons, and the distance from here to here is 1.5 meters. Okay, calculate the moment of the child about the pivot. That's really easy. That will be 400 multiplied by 1.5, 600 Newton meters anti-clockwise. Guys, it is really important that you mention it's anti-clockwise. If you just put 600 Newton meters, you're likely to get 1 out of 2, right? Because it's on the to the left of the pivot, right? So we know it creates an anti-clockwise moment, obviously, right? Right? This is anti-clockwise. So you can write the word anti-clockwise within brackets, or you can just draw the curl arrow. Either way, you just need to mention the direction. Next one. A second child sits 2 meters to the right of the pivot. Okay. Second child, 2 meters to the right. So the distance here is 2. Calculate the weight of the second child needed to balance the seesaw. Right, okay. If the child can balance the seesaw, what will happen? 400 times 1.5 should be equal to W times 2. So 400 times 1.5 is 600 is equal to W times 2. Obviously, W is equal to 300 newtons. So the second child's the weight is 300 newtons. Done. The second child now moves closer to the pivot. Explain what happens to the seesaw. Now, here's the thing, guys. The moment the second person comes closer, the moment created by the second child reduces, so it will rotate in an anti-clockwise direction. No problem, Les. I'll see you tomorrow at 5 p.m. Yeah, 5 to 7 p.m. It will rotate anti-clockwise because the 300 Newton person can only balance it at 2 meters. If the distance get less, it will go that way. Yeah, you too, Les. Good. A teacher pushes down on the left side with a force of 150 newtons at 0.5 meters. Okay. So, yeah, see tomorrow. 150 newtons, and this is half a meter. Okay. Calculate the new total clockwise, anti-clockwise moment. Okay. Now, the 600 Newton meters earlier is there. The teacher is pushing with 150 newtons at 0.5. So 150 times 0.5. That is half of 150, 75. So 675 Newton meters is the answer. Done. Understood, guys? Yeah? Because, which one are you referring to, Nanika? Which part? B, C, which one? Are you referring to part C? Because, look at this one. The second child moves closer to the pivot. Now, this child is heavier, right? 400. This guy is heavier. This child is lighter, 300. The 300 guy at 2 meters can balance. But the moment that child comes closer, the moment reduces, right? The moment on the left is bigger, so tilt. Make sense? Thumbs up or yeah, do something, guys, if you understand it. Everyone? All right, great. That's it, really. No problem. Guys, we are close to finishing this session actually now. I'm just looking at some of the other questions that I kind of got for this one. Let's see. Right. Let's do this last question, guys. This one is about static electricity, which is triple only again. So I'm going to run a timer. Again, about 2 minutes initially. We'll see. And give this a try, guys. Static electricity, again, a very popular question. And this is again triple, yeah. Good. About 1.5 minutes, guys. We'll give it a try. There are some specific words you need to use when explaining it. For example, charging by friction, right? Because there are two ways that you can charge something. You can charge by induction or you can charge by friction. Yeah. Rubbing, sometimes that kind of can be used instead of friction and you might get away with it, but friction is the better word to use. Answer this one, guys. About 40 seconds more and then we'll check. Ten more seconds, guys. We'll discuss this in a bit. Guys, just a quick reminder, like if you can just give me a like and sub, that's helpful because I'm just trying to kind of grow my channel. So that will be helpful. That's all I ask for really from you guys. That's it, right? Let's do the question. A plastic rod is rubbed with a cloth. Okay. Explain how the rod becomes negatively charged. Now, guys, initially, you have the same number of protons and electrons in both. Now, the numbers aren't realistic. Let's say you got 100 electrons and 100 protons. Let's say you got 150 electrons and 150 protons. Now, the real numbers are way bigger than this, but let's just say. Right. Now, the rod becomes negatively charged when you rub these two together. And what happens is some electrons transfer from here to there. Let's say this becomes 140. This becomes 110. Okay. Now what happens? You got 10 extra electrons, so this has a negative charge and this has a positive charge. So explain how the rod becomes negatively charged. So for part A, let me write the answer, guys. electrons are transferred to the rod from the cloth due to friction. Now there are more electrons than protons on the rod, so it becomes negative. Something to this effect, guys, and you are perfectly fine with the GCSEs at that. With that, part A done. Part B, the charged rod is held near a small piece of paper. Explain why the paper is attracted to the rod even though the paper is neutral. Now, this is a negatively charged rod, guys, okay? And you hold it close to a piece of paper. Now, what happens is there is charging by induction. It separates the charges. Now, initially, the positive and negatively charged things, say here, were evenly distributed. Now, when you bring a negatively charged rod next to it, what happens is some of these negative charges, because negative and negative repel, will move away to the other side, which means the one side, the side closer to the negative one, gets a positive charge. So what will happen now? Oppositely charged things attract, so they will attract. Part B. Part C. A charged balloon is rubbed against a jumper and sticks to a wall. Explain these terms of electric field. So what happens is, yeah, Tara, part B, you want me to explain it again, I'll do that. Now you bring a negatively charged object close to this piece of paper. Now this is negatively charged, it has electrons. The electrons here don't like it. Why? Because negatively charged things repel, right? So when the rod comes close to it, it pushes the electrons of the paper towards the other side. The end closest will induce a positive charge. That front end becomes, it looks like it's positive. Now what happens? There's negative here, there's positive here, they will attract. Right, part B. How would you explain it in terms of electric fields? Now, if you think about a balloon with a charge, let's say, okay, balloon with some negative charge. No, it doesn't say what charge it is, but let's assume it's negative. It could be positive as well, right? It doesn't say. Now, here's a wall. Now, what happens is there is an electric field around it, and those electric field lines go through this. So, at a distance, the wall feels the presence of the negative charge. So, what will happen? The negative electrons will go kind of away from it. This region, there is a charge separation, and then this region will become more positively charged. Now, what will happen? This is positive, this bit is negative, and they will stick. If you carefully put it against the wall, it will stick. If you go to the YouTube, I've seen videos on that. If you just put it like balloon sticking to wall, static electricity or physics or something, it comes up. That's how it works. Part D. A fuel tanker is earthed before unloading fuel. Explain why this is necessary. Now, if you think about, the involvement of electric field is because this is a charged particle, guys. The balloon is charged, so it has its own electric field around it, isn't it? Right? It has its electric field, like a positively charged one gives electric field lines outwards. Negatively charged one, electric field is coming inwards, right? The question doesn't specify a charge, right? About the jumper, it's the same thing. When you rub it, when the charged balloon is rubbed against the jumper, there is an electron transfer. But it doesn't say which way, because it doesn't say what is the charge it gets. If it specifies it, say if it says balloon gets negatively charged, say electrons are transferred from the jumper to the balloon, or the other way around. Yeah. Right. And the last part, guys, a fuel tank is earthed before unloading fuel. Explain why. Now, here's the thing. A fuel tank. If you think about a large, those trucks with a lot of fuel, right? Uh, you need to connect this to Earth because any charge that it has built up while it's moving, right, needs to be neutralized. So what happens is if this has any extra positive charges, electrons will come from the Earth and neutralize it. Or if this has any extra negative charges, they will flow to the Earth and neutralize it. Now the Earth, being the largest object in our vicinity, it can take or give any amount of electrons in physics. Just keep that in mind. Now, why is this necessary? Because the fuel is very flammable. So, if a spark occurs during this, due to these charges, it can lead to an explosion. So we don't need any explosion, obviously. So what we do is it is connected to the Earth. So there are usually like wires that are connected to a metal rod, and then you can just bring it and clip it to the body of the tanker so that it is earthed to make sure that any charge built up during the movement, right, when it moved through air, obviously not when it was driving, any charge built up is neutralized, minimizing the chance of an electric spark, which can be very dangerous because fuel is flammable. 3 marks. Right. I think that's quite sufficient for a day, guys. Then, so thank you for coming to the session. If you have any other things, I'm doing the AQA thing tomorrow, or just if you add it as a comment, I can help you. Right, that's it for today. Good luck for your exam on Monday and everything. I'll see you guys again. Bye, everyone. No problem. You're welcome, Ayan. Welcome, everybody. Bye bye. Thank you, Aisha. Yeah. Thank you, Tiara. Good, good, good. Yeah. Thank you. Happy to help. Bye, everybody.